Hey, welcome everyone to the AstroBit podcast, brought to you by your home for curated space news, astrobitica.com. I'm your host, Alan, the Astro Writer, and this is our very first episode of Astro Wife Asks. In this segment, my lovely wife, Raylene, say hi, Raylene.
Hi, everybody.
Will ask about an astrophysical, astronomical, or space-related subject she's curious about, and I do my best to explain it. It's a fun way to dive into the wonders of the cosmos while keeping things approachable and conversational. So without further ado, Astro Wife, what do you want to ask about today?
Well, today I would like to learn a little bit about dark matter.
Ooh.
So I would firstly like to know, what is dark matter?
Okay. We don't know. This is a short answer to that one. So dark matter, we call it dark, okay, not because it's like physically dark or it's black. It's dark because whatever it is, it doesn't interact with the electromagnetic spectrum at all, which means it doesn't reflect any light. When we look at it with all different types of telescopes and filters, it doesn't emit or reflect radio waves, microwaves, X-rays, visible light, infrared, ultraviolet, gamma rays, none of those things. So basically, in any way that we could observe matter, it is invisible to us. That's why we call it dark. But it does, the one thing it does that we can measure, it interacts with gravity. So it kind of adds gravitational force to objects that already have mass, and makes that gravitational force greater than would be expected.
So would that mean that black holes are made up of dark matter?
Well, we don't know. It's hard to tell what a black hole is really. We know how black holes form and how they begin, but we can't send a probe into a black hole to study it to know exactly what it's made of. But in relation to black holes are one way that we kind of know that dark matter exists. Okay. All right. So there's this concept in orbital mechanics, right? The closer you are to the object you are orbiting, the faster you go. And the further away from the object you're orbiting, the slower you go. Right? So think of the solar system. Mercury is the closest planet to the sun. So it orbits the sun super fast. Like a year on Mercury is just a couple days. Right? It gets all the way around. But Neptune is the furthest planet from the sun, Pluto excluded. And it takes a really long time for Pluto to get around the sun, right? Like, I don't know the exact number, but I think a year on Pluto is like several Earth years, whatever it is, right? And this theory or this concept should hold true when we look at galaxies, right? So galaxies oftentimes in the center are black holes, right? That's the massive gravitational object in the center of black holes that are holding all those stars and planets and things together. Well, it should work in that the things that are closest to the center of the galaxy, at the galactic center, should orbit faster than things on the outer edge of the galaxy, right? And this is called, we're measuring its radial velocity or rotational velocity. But what happened was, when we were looking and studying these galaxies to confirm that that was the case, we found that the outer parts of the galaxy were rotating faster than they should have been, based on how we understand gravity and how it works right now. So that concept that holds true in the solar system doesn't hold true when we look at galaxies. The outer parts of the galaxies rotate a lot faster than they should be.
So you said dark matter responds to gravity, right? Or it has a lot of gravity.
Yeah, it interacts with gravity.
Interacts with gravity. Okay, so would that mean that galaxies on the outside would then have dark matter if it spins faster?
Well, we think the dark matter is spread kind of uniformly throughout the galaxy, or the galaxies that we're observing, and that's why that they're spinning the way that they are. Now, there is a opposing view to this, right? There are a handful of scientists that believe in what's called modified Newtonian Dynamics, or MOND. And what MOND says, basically they're saying that there is no dark matter, that it's not really there, that what we are doing wrong is how we calculate gravity, right? And how we measure gravity, that we've got that wrong. So one way to think about it is the effects that the gravitational pull of an object has on you is really strong when you're up close to it, right? Obviously. And then the further away you get from it, the effects of gravity on you are much less and less and less until the point that you get so far away from that object that it has no gravitational effect on you whatsoever. That is what like traditional Newtonian physics tells us. But MOND says that actually, no matter how far away you are, you could be on the other side of the universe from that object, it still has some gravitational effect on you, even if it's almost immeasurable. And that would account for why the outer portions of these galaxies would rotate faster, because the gravitational effect is stronger from the black hole or whatever the massive gravitational object is in the center of that galaxy is, right? But one criticism is the people that support MOND, they've only done a small study. They've sampled like 150 galaxies. And while, 150 sounds like a lot, in a sample size where we know of billions of galaxies in the universe, 150 is a really small sample size. So while it holds true for a small study, it has yet to be explored on a much larger study with a much larger sample size.
So we don't really know what dark matter is, and there's argument of whether it actually exists, correct?
Yes. And another counterpoint to the MOND people, the people that support that dark matter exists, is called the bullet cluster or the bullet galaxy. All right. So the bullet cluster is actually a galaxy that was formed from the collision of a handful of 2 or 3 smaller galaxies. We don't really know the total number. We know it's like at least 2, right? Because galaxies merge and collide. It happens all the time. And when we look at the bullet cluster, and there's this thing that we have, it's called gravitational lensing. You ever heard of that?
No.
Okay. So gravitational lensing is when there's an object behind another object, right? Or so you're trying to observe an object, but there's something between you and it. Well, if that thing that's between you and the object you're looking for is gravitationally dense enough, what it might do is bend the light coming from that object that you're trying to observe and like bend it around itself so that you can see it, right? So imagine there's, a person you want to observe, but there's a large building between you and that person. Well, if that building had enough gravitational force, it might bend the light that's reflecting or emitting off the person you want to see, bend it around the building so that it can come and hit your eyes. That's called gravitational lensing. And we use this all the time. So when we look at the bullet galaxy, it is bending the light of the objects behind it much greater than it should be based on the observable mass that we see there. So when we look at, estimate how many stars and possible planets are in the bullet cluster, we can estimate how much gravitational force it should have, but it is bending the light as if it had much greater gravitational force than it should. So we attribute that to dark matter again. Something that's not visible, something that we can't see, is adding gravitational mass to the bullet cluster, allowing it to bend the light through gravitational lensing of the objects behind it so that we can see those objects.
That's very interesting.
Yeah. So while the debate is still out there on, whether MOND is real or if dark matter is real, still remains to be seen. But it is an active area in astrophysical and cosmological studies.
Very cool.
Okay. Anything else on dark matter?
No, that pretty much clears it up for me. The different bodies of thought are very interesting on, what it is and why it's there. So, thank you.
Yeah, it's always big news in the astrophysical community when one or the other side releases a new paper that supports their argument. It becomes like the hottest thing in astronomy for about a week or two until people get a chance to dissect it. And ultimately, we always go back to the same thing. Well, there's not enough evidence to prove it, but there's also not enough evidence to disprove it yet. So what do you think? Do you think dark matter exists?
I think it does, because it helps explain a lot of the phenomenon that we can't explain ourselves. And I like the idea of having something out there to be able to explain what's happening, even if you can't entirely prove it. Because if there's an absence of dark matter, for example, then that doesn't explain a lot of the phenomenon that happens in space. So by accepting the theory of dark matter, because you said we can't prove it yet, by accepting the theory, it helps explain a lot further on what we're seeing or what we're observing or what we're studying.
Yeah, because even if we bought MOND, modified Newtonian dynamics, as true, well, that explains the radial velocity or the rotational velocity of galaxies, but that doesn't explain the gravitational lensing from the bullet galaxy, right? So I think it's safe to say that dark matter probably exists for now until something else comes along, but that is where most of the evidence is right now. Cool. All right.
Oh, thank you. That was very interesting. I learned something new today.
Yes, I hope you did too. Thanks so much for tuning into this episode of the AstroBit podcast and our first ever Astro Wife Asks. Hope you enjoyed our conversation and maybe learned something new along the way. If you want to explore more curated space news, don't forget to check out astrobitica.com and follow us for updates and future episodes. Until next time, keep looking up and stay curious.